The Alexander cell, understanding corrosion monitoring. Introduction. Corrosion is an electrochemical process that gradually degrades metal. However, it can be controlled or even stopped by lowering the electrical potential of the metal below its corrosion level. The Alexander cell is a device designed to monitor this process by detecting the direction and strength of the corrosion current, helping to determine whether cathodic protection is effective or not. How the Alexander cell works. The Alexander cell operates by creating a controlled corrosion environment. It includes an earth path that allows the device to be influenced by current from a cathodic protection system. When in use, this influence can be observed through a current meter, an ammeter, showing whether corrosion is occurring or being prevented. The device consists of 4 electrodes, 2 at the top and 2 at the base. One top electrode is cleaned to bright metal, which makes it active, anodic, while the other remains passive, cathodic. When an electrolyte sample bridges these 2 electrodes, a corrosion reaction begins at the bright steel electrode. This reaction generates a current that flows through the meter, then through the base electrodes, which are also cleaned to ensure equal reaction with the surrounding ground. The circuit is completed as the current returns to the top electrode through the system. The equilibrium of the cell, when placed on the ground with electrolyte, the Alexander cell establishes a dynamic equilibrium. The base electrodes behave equally due to identical preparation, while the top electrodes create a potential difference that drives corrosion current. When connected to a pipeline under the cathodic protection system, the system changes. If protection is insufficient, the corrosion continues in the Alexander cell. If protection is sufficient, the current opposes and eventually reverses direction in the Alexander cell, which is shown on the microammeter. This reversal is visible on the meter and indicates that corrosion has been stopped. This is seen as it happens. It is dynamic. Computer modelling. The Alexander cell can be simulated using software such as Excel. In these models, multiple corrosion cells interact with a cathodic protection system. By adjusting variables like transformer rectifier output, the users can observe how corrosion can be reduced or eliminated. This behaviour follows Faraday's laws, which link the amount of metal lost to the electrical current flowing through the system. Procedure for use. Clean the 2 base electrodes and place them on the ground near the pipeline. Clean the top anode and connect the meter. Place an electrolyte sample between the top electrodes. Observe and record the current's direction and strength. This can be done on a data logger automatically. Connect the cell to the pipeline and monitor any changes in the current. This is dynamic, so if you have somebody at the transformer rectifier to adjust the amount of current being discharged, this will show immediately whilst you are making this measurement. Interpretation of the results. Initially, the current measured is caused by corrosion in the Alexander cell. When the cell is connected to a properly protected pipeline, if the current stops or reverses, corrosion has been prevented. A reversal current indicates that protection is overpowering the corrosion process in the Alexander cell. Since corrosion is the only source of the original current, its disappearance confirms that the reaction has stopped. Any reverse current is due to the protective current flowing back to the system. Conclusion. The Alexander cell is a practical and effective tool for determining corrosion and the performance of the cathodic protection systems. By simply observing current direction and magnitude, it provides clear evidence whether corrosion is active or has been successfully controlled. This device can also be used to assess the effectiveness of the control of corrosion noise. It is the only device that can do this.